Hello everyone, myself Prashant from BSC Chemistry Honors first year. Today we are gonna read chapter Stereochemistry of Organic Compounds. So here we go. Isomerism. Compounds which have the same molecular formula but have different properties are called isomers, and the phenomenon is called as isomerism. The difference in the properties of isomers is due to the difference in the relative arrangement of atoms and their molecules. Types of isomerism. There are two types of isomerism: structural isomerism and space or stereoisomerism. These are further classified into various types as shown below. Isomerism, there is structural isomerism and stereoisomerism. Here stereoisomerism have further parts: configurational stereoisomerism and conformational isomerism. And configurational stereoisomerism have two parts: optical isomerism and geometrical isomerism, where structural isomerism have six parts: chain or nuclear isomerism, position isomerism, functional isomerism, metamerism, ring chain isomerism, tautomerism. So we discuss them further in details. Structural isomerism. Compounds having the same molecular formula but different structural formula are known as structural isomers, and the phenomenon is known as structural isomerism. This type of isomerism arises due to the difference in the arrangement of atoms within the molecule having the same molecular formula. Various types of structural isomerism are: chain or nuclear isomerism. Compounds having the same molecular formula but which differ only in the arrangement of carbon atoms in a chain are known as chain or nuclear isomers, and the phenomenon is known as chain or nuclear isomerism. For example, there are three chain isomerism having molecular formula C5H12. Here we can see N-pentene, isopentene, neopentene. Position isomerism. This type of isomerism is said to exist in compounds which have the same molecular formula but differ in the position of attachment of a characteristic group or atom. For example, N-propyl chloride and isopropyl chloride both have the same molecular formula C3H7Cl but differ from each other only in the position of attachment of the chloride atom. N-propyl chloride, isopropyl chloride. You can see the difference. Next is functional isomerism. This type of isomerism is due to the presence of different structural groups in compounds having the same molecular formula. For example, both alcohols and ethers have the same general formula CnH2n plus 2O but differ in the nature of functional groups. For instance, C2H6O represent the following two compounds: ethyl alcohol and dimethyl ether. Metamerism. This type of isomerism arises due to the difference in the distribution of carbon atoms on either side of the functional group in compounds having the same molecular formula. For example, diethyl ketone and methyl propyl ketone represent a pair of metamers having the molecular formula C5H10O. Diethyl ketone, methyl propyl ketone. Some characters, some general concept concerning optical isomerism. A plane polarized light. Ordinary ray of light consists of waves of different wavelength having vibrations in all planes at right angles to the direction in which it travels. Monochromatic light consists of waves having only one wavelength, but even such a ray has its vibrations in all planes. Plane polarized light. When a monochromatic beam of light is allowed to pass through a nickel prism, a special prism made of silate crystals CaCO3, then the emergent beam of light is found to have vibration in only one plane. Thus, the light whose vibrations take place in only one plane is known as plane polarized light, and the plane along which the vibrations take place is known as plane polarized light. The nickel prism used for polarizing light is known as polarizer. Is a source of light, and polarized light, polarizer, polarized light. Figure shows the vibrations in ordinary and polarized forms of light. Optical activity. Substances which can rotate the plane polarized light are said to be optically active, and the property is called optical activity. Optically active substances are two types: dextrorotatory and levorotatory. Dextrorotatory, designated by D or plus. Substances which rotate the plane polarized light towards right are termed as dextrorotatory. Levorotatory, designated by L or negative. Substances which rotate the plane polarized light towards the left are termed as levorotatory. Molecular celerity. Chiral structures. A structure is said to be chiral if it cannot be superimposed on its mirror image and the property is called celerity. One may describe celerity in terms of symmetry elements of the molecules under study. Celerity is primarily related to the lack of plane, sigma, and center of symmetry in the molecule. A simple example of chiral object is human hand, which neither has a plane or center of symmetry and thus is non-superimposable on its mirror image. Figure shows non-superimposable mirror images, object and image. There is the mirror in between them. So next we are going to discuss carbon bonded to four different substituents is chiral. For example, lactic acid has a chiral carbon atom marked star is chiral. This one is chiral carbon. This one lactic acid non-superimposable mirror images. Optical isomerism. Isomers which resemble one another in their chemical reactions and most of the physical properties but differ in their effect on a plane polarized light are called optical isomers, and the phenomenon is called as optical isomerism. Type of optical isomerism: enantiomerism, diastereomerism. Enantiomers or mirror image isomerism. Isomers which are non-superimposable mirror images of each other and rotate the plane of polarized light equally but in different directions are known as enantiomers or enantiomorphs, and the phenomenon of mirror image isomerism is called enantiomerism. Fundamental conditions of enantiomerism: celerity. The property of existing as non-superimposable mirror images is the fundamental and only condition of enantiomerism. Molecule is termed as chiral if it does not have a plane or center of alternating axis of symmetry and is therefore non-superimposable on its mirror image. Celerity is one of the most enantiomeric molecules due to the presence of at least one chiral carbon atom. Carbon atoms of the type C carbon A, B, C, D, the one which is bounded to the four different substituents, for example, lactic acid. At the same time, there are molecules like allenes and biphenyls which do not contain any chiral carbon atom, but they still possess the property of celerity and thus exhibit enantiomerism. Characteristics of enantiomers: they have identical physical properties like melting points, boiling point, refractive indexes, solubilities, etc. The only difference in the direction of a rotation of plane polarized light. Even the magnitude of rotation is same. For example, specific rotation of 2 enantiomeric 2-methyl 1-butanol is plus 5.76 and minus negative 5.76 respectively. They have identical chemical properties but different in their rates of reaction towards other optical active substances. For example, chemical reaction of lactic acid are exactly the same of those negative lactic acid. Even the speed of reaction is same. But when made to react with some optically active compound like its esterification with plus secondary butyl alcohol, then the rate of esterification plus lactic acid is different from the negative lactic acid even with the same alcohol. They have different biological properties. For example, plus tartaric acid is readily consumed by the mole penicillium gallicum, while its form is not. Also, dextroglucose is metabolized by animals, by liver form is not metabolized at all. When equal amounts of two enantiomers are mixed together, it results in the formation of an optically inactive form called racemic modification or racemate or racemic mixture. Since optical activity is one of type of enantiomer is cancelled by equal number of other type, net result is optically inactive mixture. Diastereomerism. Chiral and achiral molecules with two stereogenic centers. Compounds containing one stereogenic center exist in two stereoisomeric forms. Compounds with two dissimilar chiral carbon atoms exist in four stereoisomeric forms. For example, the four stereoisomers of 2,3-dichloropentane are shown as figure 1, 2, 3, and 4. Enantiomeric pairs, which are non-superimposable mirror images of each other, are 1, 2, and the second pair is 3, 4. Let us compare 1 and 3. We can see it may be seen that the two forms are neither completely identical nor completely mirror images of each other. Such stereoisomers are diastereomers. Comparison of enantiomers and diastereomers. Enantiomers. These are stereoisomers which exhibit mirror image relationship. Diastomers, these are stereoisomers which do not have a mirror image relationship. Enantiomers, they have similar physical properties. Diastomers, they have different physical properties. Enantiomers, they cannot be separated from each other by physical processes. And in diastomers, they can be separated by physical methods like fractional distillation, crystallization, chromatography, etc. Enantiomers. They have identical chemical properties but differ in the rates of reaction with optically active compounds. In diastomers, they have similar but not identical chemical properties. Their rates of the reaction even with the particular reagent are different. In enantiomers, the extent of optical rotation is same but direction are different. In diastomers, stereomers, they have optical rotation in the same or different direction but the magnitude is always different. Next, through and through diastereomers. It is a system of nomenclature used for distinguishing two diastereomers. The system of applicable only when two groups attached to the to one stereogenic center are the same as two groups attached to the other stereogenic center. The method is derived from the name of two diastereomeric carbohydrates, ethros and threose. Here we can see if two groups are on the same side in the Fisher projection formula, then the diastereomer is designated as isomer. If the two groups are on the opposite side of Fisher formula, then the diastereomer is designated as isomer. Next, comparison of external and internal compensation. External compensation. It is due to mirror image relationship between the structures of two enantiomeric molecules. Internal compensation. It is due to the mirror image relationship between the structure of two halves of the same molecule. External compensation. One enantiomer cancels the rotation of the other enantiomer, and in internal compensation, one half of molecule cancels the rotation of the other half. In external compensation, racemate formed presents a mixture of two isomeric compounds. In internal compensation, meso compound represents a single pure bond compound. In external compensation, it is a reversible process. The racemic mixture can be resolved into and its uh, plus and negative enantiomers. Internal compensation, it is a permanent effect. It is not possible to resolve a meso compound into a optical active forms. External, both complete and partial external compensation is possible. Partial internal compensation is not possible. Next, inversion and retention of configuration. If an atom or group of atoms directly attached to a chiral center is substituted by some other atom or group, then the configuration of the new compound is sometimes found to be different from that of the starting parent compound. This is known as optical inversion of configuration, as the phenomenon was discovered by Walden. Therefore, the phenomenon is also termed as Walden inversion. It is generally observed as in SN2 reaction where an incoming nucleophile displaces the bonded nucleophile through Beck's attack. For example, when treated with aqueous KOH, iodobromoctane gives this compound with an opposite configuration. Here we can see the reaction. However, if a compound containing a chiral center is converted into a new compound without breaking any of the bonds with the chiral center, then the product is found to have same configuration as the starting parent compound. This means that the reaction proceeds with retention of configuration. For example, this reaction can be taken as the example. Third, D and L system of nomenclature. D and L nomenclature is a system to determine the relative configuration of compounds. The reference compound chosen was glyceraldehyde, and configuration of its two enantiomers designated by the symbol D and L were assigned the following configuration as proposed by M. L. Fisher. Here we can see three-dimensional of a planar representation of two enantiomers of glyceraldehyde. Nomenclature of geometrical isomers. Cis and trans system of nomenclature. The isomer in which similar groups are present on the same side of a double bond are denoted by using the prefix cis before the name of the compound. Cis and same side. The isomer in which similar groups are present on opposite sides of the double bond are denoted by using the prefix trans before the name of the compound. Example: cis-2-butane, trans-2-butane. Cis-1,2-dibromoethane, trans-1,2-dibromoethane. Limitation of this is the cis and trans system of nomenclature cannot be employed in case of compounds where all the four substituents attached to double bonded carbon atoms are altogether different. In compounds of type carbon-carbon D, for example, this. Okay, E and Z system of nomenclature. This system of nomenclature is based upon the sequence rules originally developed by Can, Ingold and Prelog for assignment of configuration of optical isomerism. For assigning configuration to geometrical isomers, first the two atoms or groups bonded to each doubly bonded carbon atoms are assigned a higher or lower priority according to the priority sequence rules, which were developed for R and S system of nomenclature of optical isomers. The isomer in which the higher priority atoms groups are present on the same side of the double bond is designated as Z. The isomer in which the higher probability atoms groups are present on opposite sides of the double bond is designated as this E. Example: 1 bromo 2 chloro 2 fluoro 1 iodoethane. The Fischer projection. A simplification of the flying wedge representation is the Fischer projection in which various groups attached to the chiral carbon atom are projected in the form of cross so that horizontal lines represent bonds pointing towards the observer and vertical lines represents the bond pointing away from the observer. The vertical part represents the longest chain of carbon atom with the highly oxidized functional group at the top and is numbered as carbon 1 according to IUPAC. The chiral carbon atom is not written is located where the horizontal and vertical lines cross each other. A, B, C, D. Fischer projection. For example, the flying wedge and Fischer projection formula of 2 lactic acid enantiomer are shown as this is flying wedge and this is Fischer projection R lactic acid, S lactic acid. You can see. Next is the Sawhorse perspective formula. The Sawhorse formula indicates the special arrangement of all the ligands on two adjacent atoms. The bond between the adjacent carbon atom is represented by a diagonal line, usually from lower left to upper right. The left hand bottom and represents the atom nearest to the observer, and the right hand top and the atom that is farther away. Two of the remaining bonds to the atom are drawn vertically and the other four at +120 degree and -120 degree angle of these as shown. Here we can see the Sawhorse conformations of ethane. We can see this staggered form and this is eclipse form. Newman projection is the Newman projection. Just as the Fischer projection is planar projection of the flying wedge formula, the Newman projection is a planar projection of the Sawhorse formula. Similar to the Sawhorse projection, Newman formula also represents the special arrangement of all the ligands on two adjacent atoms. Here, a molecule is viewed along the axis of carbon-carbon bond. The carbon atom towards the front is represented by a dot and carbon atom towards the rear by a circle. The ligands of carbon atoms are shown as being bonded to the dot or circle. For example, staggered conformation of ethane, eclipse conformation of ethane. H atom or rear carbon directly behind this. So here's the difference between conformation and configuration. In conformation, these are the 3D arrangements in space of the atoms in a molecule which are inconvertibly by rotation around the single bond. In configuration, these are the 3D arrangements in space of the atoms in a molecule which are not inconvertible by rotation around the single bond. In conformations, for example, eclipse and staggered conformations of ethane are readily inconvertible by rotation around carbon-carbon single bond. We can see for and in configuration, for example, the configurations of lactic acid and lactic acid are inconvertible by rotation about a bond. We can see the figures. In conformation, the interconversion does not require breaking of and making of bond. In configuration, the interconversion is possible only through the breaking and making of the bonds. Conformational analysis of ethane. The molecules of saturated acyclic compounds can assume an infinite number of conformations due to rotation about carbon-carbon single bond. However, it must be noted that the rotation around the single bond is not completely free and potential energy of the molecule changes somewhat with rotation around the carbon-carbon single bond. And as such, the potential energy of a different conformation is also not the same. Thus, the study of the energy changes which occur in the molecule due to the rotation of around carbon-carbon single bonds in known as conformational analysis. The other conformations of ethane can be specified by dihedral angle, which is the angle between the carbon hydrogen bond on the front carbon and carbon hydrogen bond on the rear carbon atom in Newman projection. Here we can see Newman projections, and there is Sahos projection. The conformation is in which the hydrogen atoms are as far apart as possible and theta is equal to 60 degree is called the staggered conformation, whereas the conformation with theta is equal to 0 degree is called the eclipsed conformation because the H atoms on the rear carbon are eclipsed, i.e. as close as possible to the hydrogen atoms on the front carbon. Any other intermediate conformation is called as skew conformation. Conformations of cyclohexane. This is our the new next topic. Two most important non-planar models possibly in which all bond angles are 109 degrees so that systems are free of Bayer strain are chair conformation, a rigid form, board conformation, flexible form, and symmetrical. Chair conformation of cyclohexane. It is the most stable form. All the bonds are staggered, thus Pitzer strain is minimized. All the bonds angles are not exactly tetrahedral, but 111 degrees of free of Bayer strain as well. However, there are Gaussian-butane-like interaction between neighboring methylene groups leading to the slight steric strain. Dihedral angles theta are not exactly 60 degree but 56 degree, causing slight flattening in the ring. Here we can see the structures using precision ball and stick model, Newman projection formula, chair conformation of cyclohexane. Boat conformation of cyclohexane. There is no angle strain in the boat conformation since all the angles in it are tetrahedral, but there is complete eclipsing of the hydrogens on four of the side of carbon C1, C5, 3, C5 and C6, leading to a considerable torsional strain. The inside of hydrogen and carbon 1 and carbon 4, the flagpole hydrogen interface with each other sterically is translunar interaction. The flagpole hydrogen atoms lie only 1.83 angstrom apart while the sum of the van der Waals radii is 2.53 angstrom. 2.5 angstrom. This gives rise to van der Waals force strain in the molecule. Due to torsional and van der Waals strain in it, the boat conformation is less stable than the chair conformation. Twist bond or skew boat conformation. Twist bond is released from the boat from when we hold C2 and C3 of the boat form in one hand and C4 and C5 in the other and twist the molecule so that C3 and C6 go down while C2 and C5 come up. During this twisting, the flagpole hydrogen on C1 and C4 marked HA and HB in figure move apart and at the same time the two hydrogen on C3 and C marked CHC and HD in figure move closer together. In the twist boat conformation, the distance between HA and HB is equal to that between HC and HD. Thus, in this conformation, the van der Waals strain between flagpole hydrogen is reduced to a minimum. At the same time, the torsional strain on C2 and C3, C5 and C6 is also appreciably reduced. As result, the twist boat is more stable than that of boat formed by about 1.4 kcal molecule inverse, although it is still less stable than the chain conformation by about 5.5 kmol. As we can see in the structure, half chair conformation. In between the chair and twist boat conformation lies yet another conformation known as the half-chair conformation. In fact, it represents a transition state conformation. It has both the angle and torsional strains and is about 11 kcal per mole higher energy than the chair form, the half-chair conformation. Some questions for practice, and that's all. The chapter ends here. Thank you.